So today we're going to talk about torque and static equilibrium. Our scenario is that we have a man standing on a ladder, and the ladder is resting against a window, which I'll call W, and the floor, which I'll call F. And the system is at rest, or in other words, it's at static equilibrium, which simply means that the sum of the forces and the sum of the torques are equal to 0. So there's no overall acceleration of the system. It's just like the fact that I'm standing here and there are forces acting on me. For example, there's the normal force pointing straight up, which is keeping me from falling through the floor. And then there's a force of gravity, my weight, which is pulling me down. But those two forces happen to perfectly cancel out, such that there's no net acceleration of my center of mass, at least relative to the ground. And so that's what's happening here. There are still forces at play, and in fact there are still torques at play too. However, we know that they will be of such magnitudes that they perfectly cancel each other out, and so there is no net torque or no net acceleration on the system. So the way we're going to approach this problem, first of all, what they want us to find is the normal force that the wall is imparting on the ladder, so this reaction force up here. And so the way we're going to do that is by considering the torque that each object or each force that we'll find is applying to this system. If we consider it, sort of a pivot point here and ask ourselves, okay, well, if the man's standing here, then his weight is going to sort of cause this ladder to start to rotate in this direction, right? In the clockwise direction, this way. So let's see if we can use this equation and what we know about torque to solve the problem. So let's start with a free body diagram and put in all the forces that we have to worry about. First of all, we have the man. He has a mass, he has a weight. So there's going to be some force M, mass of the man, times gravity, pointing straight down. Furthermore, we have the ladder, which has a weight. We'll take that weight to be at about its center of mass, which is just halfway along the ladder. So call mass of the ladder times G. I'm assuming the ladder is uniform, and so its center of mass is just at the halfway point. So if the ladder is 5 meters long, then this halfway point is just 2.5 meters. Okay, so those are the easy ones. Now, we're told that we're asked to find the normal force here, and we remember that normal forces act at perpendiculars to the surface at which they're acting. So here, the surface is vertical, so the normal force is perpendicular to that horizontal. So I'll call that N sub W, normal force from the window. We are told we can neglect the friction along the window. Otherwise, there would, in general, be a frictional force here, and I suppose it would be acting upwards, resisting the ladder from slipping down this way. But here we're told to neglect it. And finally, down here, we have, by the same argument, a perpendicular normal force acting straight up, so I'll call N sub F, normal force from the floor. And if we were to stop here, there would be a problem, because we're assuming that the system is in static equilibrium, and what that means is that the sum of forces in all directions is 0, including the x direction, for example. But if we consider what forces we have at play in the x direction, and by x I mean horizontal, the only force is this normal force from the wall. And so if this were the only force at play, the system would accelerate to the left. But we're assuming that the sum of the forces, and therefore the acceleration, is 0. So we have to have another force counteracting that. And that force will be the force of friction at the bottom. So we're neglecting friction up here, but we can't neglect the friction down here. So we have a force of friction, which is resisting this normal force from the wall. And so now we're in a good position to start analyzing the torques. So let's start with the the man, for example. Now, if you remember, the torque in general, which is a vector, but let's worry about the magnitude for now, is the cross product of r and f in general, where r is a radial vector from the axis of rotation. So a vector that starts here and points to wherever the force is acting. And f is the force at play. So in this case, it would be mmg. Now, we can simplify our lives quite a bit. So if we break that force into components. Now, the thing about torques is that the only way you can impart torque on an object is with a perpendicular force. So in fact, if we broke this into components along the direction of the ladder, just if we wanted to, it's totally arbitrary. But let's say we did that. The only component that's providing any torque at all is this component here, the perpendicular component. This component of his weight, which points this way, parallel to the ladder, imparts no torque on the system. So instead of worrying about complicated cross products formulas, what we can do is just break our forces into their components and take the perpendicular force as our torque. So what I could write instead is this is, r times f perpendicular. We have to worry about the direction, but we can tell that from our free body diagram. So if this is an angle theta, then this is 90 minus theta in here. And if this is also a right angle, this guy here must be theta. And so this perpendicular component is mmg cos theta. We don't really care about this guy. mmg here, I meant this vector. We don't really care about this one here, which would be the sine, because again, it imparts no torque. So now if we think about what is the torque of the man, well, it's going to be r, which is the distance from the axis of rotation to wherever the force is acting. In this case, it's 3 meters. So it's 3 times the perpendicular component of that force. Well, in that case, it's in this case, it's mmg cos theta. And we're almost done, but now we have to make a choice. And the choice is basically a convention for which direction, clockwise or counterclockwise, we take as positive. So because this man, his weight, is causing a torque in the clockwise direction, let's take clockwise as positive. So what I mean by that is, this man is imparting a positive torque. This ladder will also, as we'll see, impart positive torque. But this force here, which will have a component upwards, perpendicular to the ladder, will impart a negative torque. And it doesn't matter which direction you choose as positive overall, but you have to make sure that you're consistent with each force when we sum them. Otherwise, we're going to get the question wrong. So in the same way, if I just erase this for clarity, in the same way that we got this perpendicular component, let's do that for the ladder. So if I break, let me just redraw this like that. If we break the ladder's forces into components, we are interested in the perpendicular component, which is this guy here. And again, if that's theta, then this is theta. So this guy here, I'll just write it up here, is mlg cos theta. That component there. And so the torque imparted by the ladder, which I'll call torque ladder, is that radial distance. Now it's from here to where the ladder's center of mass is, which is 2.5 meters along the ladder. 2.5 mass of the ladder, g cos theta. and it's positive, just like this guy, because they're both causing a clockwise torque. We're almost done because, well, we'll see why. So let's break this normal force from the window into its components, okay? So if we do that, we are interested again in the perpendicular component, which is this guy here, perpendicular to the radial vector. So with a bit of trigonometry, we can show that that's theta, and therefore this is theta. And so this guy here, if this vector is n sub w, then this vector here is n sub w sine theta. And so our torque from the window is nothing more than the length of the ladder, because that's the radial vector's magnitude, it's 5 meters. 5 times that component of the normal force, which is n sub w sine theta. But wait, we have 2 more forces to worry about. Sort of, but we'll see that actually these don't apply any torque to the ladder. And one way to see that as well, if our equation for torque is the radial vector times the perpendicular component of the force, the radial vector for n sub f and f sub f is 0. And so there's no torque imparted by these 2 vectors. And so all we have to do now is apply this equation here. But I made a bit of a mistake because I forgot that I needed to include a minus sign here. And the reason I have to include a minus sign here is because I've chosen clockwise as positive. But this force here is, if you think about it as what kind of torque would this force impart on the ladder? Well, it would cause the ladder to start to rotate this direction, in the counterclockwise direction. And so that's in the opposite sense to what these forces are doing. And so we must have a minus sign there. So now if we sum our forces, well, we know that if I just apply this equation, tau m plus tau l plus tau w is 0. And I can plug in my numbers. 3. Well, I'm running out of room, but this guy's going to be equal to 0. And so we don't need to bother going through all the math or through the algebra, but if I gave you a mm and I gave you an ml, then we can solve for n sub w, because we know what g is and we know what this theta is just by trigonometry. And if you just look at it for a second, you can see that it has to be 60 degrees. But yeah, that's all I wanted to go over. This is a static equilibrium problem. And so the moral of the story is break each force that's imparted into its perpendicular and parallel components relative to the radial vector, relative to the vector starting at the axis of rotation and pointing to wherever the force is being applied. And then take the torque as the product of that magnitude of the radial vector times the component of the perpendicular force, or the perpendicular component of the force. And then make sure you get the correct sign according to whatever convention you choose, and then apply the formula for static equilibrium, which simply says that the angular acceleration is 0. So yeah, I hope you learned something.